Close your eyes. Let the sounds of the present fade. The traffic, the hum of the refrigerator, the distant world of clocks and obligations. Let all of it recede, gently, the way sound recedes when you move into deep water. Let the darkness behind your eyes become a different darkness, older, deeper, a darkness that existed before you, before your civilization, before your species, before the forests and the flowers and the birds, before almost everything you know as the living world. We are going back tonight, further than last time, further than the dinosaurs, further than the first forests, further than the first fish. We are going back 445 million years to the end of the Ordovician period, to the first great catastrophe in the history of complex animal life, to the moment when the world, still young by geological standards, still only recently populated by the extraordinary creatures of the Cambrian explosion and the Ordovician biodiversification, nearly ended for the first time. There had been extinctions before. Life has always died, species by species, lineage by lineage, the slow background turnover of evolution. But what happened 445 million years ago was different. It was not the background. It was not the ordinary slow cycling of species. It was a catastrophe sudden by geological standards, global in its reach, merciless in its selectivity. It killed approximately 85% of all marine species. It ended lineages that had existed for hundreds of millions of years. It silenced reefs that had been growing since before the Cambrian. It emptied the shallow seas that had been the richest and most diverse environments on Earth, and left them bare and cold and almost lifeless. It is called the late Ordovician mass extinction. Geologists sometimes call it, by its stages, the Endcatian and Hernantian extinctions, the two pulses of killing that together make up the first of the 5 great mass extinctions in the history of animal life. It is the least famous of the 5. It is overshadowed by the Permian extinction that killed 90% of everything, by the Cretaceous extinction that killed the dinosaurs, but it was the first. And in some ways, it was the most astonishing, because it happened to a world that had never experienced anything like it before. A world that had no evolutionary memory of mass extinction. A world that was caught utterly unprepared. Tonight, you will descend into that world. You will stand on the floor of the Ordovician Sea and look up through clear, warm, shallow water at a sky you cannot breathe. You will watch the glaciers advance across Gondwana, thousands of kilometers to the south, and feel the cold they send northward into the warm tropical seas. You will see the water level fall, and the reefs exposed to air they cannot survive, and the communities of creatures that had taken tens of millions of years to assemble, dissolving in the cold and the dark and the oxygen-poor water. And then you will watch something else. You will watch the survivors, the ones that found the deep water, or the cold water, or the oxygen that remained, the ones that were small enough and tough enough and adaptable enough to make it through the worst that the first great ice age of the animal world could throw at them. And you will watch, slowly, over the tens of millions of years that followed, as those survivors built a new world from the ruins of the old one. The first apocalypse, the first survival, the first recovery. Let your breathing slow. Let the weight of 445 million years settle over you, gently, like sediment settling through still water. And let us begin what the Ordovician world was, The Ordovician period began approximately 485 million years ago at the close of the Cambrian, and it lasted for about 45 million years, ending 444 million years ago in the extinction that is the subject of our story tonight. 45 million years is a long time. It is longer than the interval between the extinction of the non-avian dinosaurs and the present day. In those 45 million years, the world changed enormously, and life diversified into a complexity and richness that the earlier Cambrian world had only hinted at. The geography of the Ordovician world was dramatically different from anything we know. The arrangement of the continents was almost the reverse of today's. The great landmass of Gondwana assembled from what would one day become South America, Africa, Antarctica, India, and Australia dominated the southern hemisphere, extending from the tropics all the way to the South Pole. It was the largest landmass on Earth, a vast, continuous supercontinent whose presence dominated the climate and the ocean circulation patterns of the entire planet. The other major land masses of the Ordovician were smaller and more scattered. Laurentia, the ancient core of North America, sat in the tropics, straddling the equator, its southern shores lapped by warm, clear, shallow water. Baltica, the core of northern Europe, was in the mid-latitudes of the southern hemisphere, slowly drifting northward. Siberia was its own separate continent, positioned in the tropics north of Gondwana. Various smaller terrains and island arcs were scattered across the Iapetus Ocean, the ocean that lay between Laurentia and Baltica, the predecessor of the Atlantic, and across the vast Panthalassa, the ocean that covered most of the northern hemisphere. There were no mountains of the scale we know today. The great mountain ranges of the modern world, the Himalayas, the Andes, the Rockies, the Alps, were all tens of millions of years in the future, waiting for continental collisions that had not yet happened. The Ordovician landscape was lower, more worn, more uniformly topographically subdued. The highest points on the continents were the remnants of older mountain ranges, slowly being eroded by rain and wind to low, rounded hills. The sea level in the Ordovician was high, very high. The continents were flooded with vast, shallow seas, epicontinental seas, the geologists call them, seas that covered the interior of the continental platforms to depths of a few tens of meters. North America, in the Ordovician, was largely submerged. The rocks of the mid-continent, the limestone and dolomite formations of Ohio and Missouri and Kansas, are the accumulated shells and sediments of those ancient shallow seas, deposited when Cincinnati was the floor of a warm, clear, tropical ocean teeming with life. The climate of the Ordovician was, for most of its duration, warm, warmer than today, with no permanent polar ice. The greenhouse conditions that had characterized the Cambrian continued into the Ordovician, with high atmospheric CO2 levels and a global average temperature well above what we experience today. The tropics where Laurentia and parts of Gondwana lay were exceptionally warm, their shallow seas bathed in sunlight, their waters clear and carbonate-rich, ideal for the growth of the shell-bearing organisms that were the dominant life forms of the Ordovician. The atmosphere of the Ordovician was alien to us. The oxygen level was rising, driven by photosynthesis, but it was still below the modern level, perhaps 70% of what we breathe today. There was no ozone layer of the strength we know, because ozone is made of oxygen, and the oxygen level was lower. Ultraviolet radiation was correspondingly higher at the surface than today. The land was largely bare of large life. The first primitive land plants were barely establishing themselves on the wettest margins of the continents, and the first land animals were only beginning to venture out of the water. The continents, from a distance, would have looked brown and gray and red bare rock and wind-blown sediment, without the green of forests or the gold of grasslands. Everything that mattered in the Ordovician happened in the sea of 1,000 shells. The Ordovician Sea was one of the most biologically productive and diverse environments in the history of life on Earth. The Great Ordovician Biodiversification Event, the dramatic expansion of marine animal diversity that characterizes the Middle Ordovician, produced a world of extraordinary richness in a geological eye blink. Within a few tens of millions of years, the number of marine genera roughly quadrupled, and the ecological complexity of marine communities increased dramatically. The dominant creatures of this world were animals that are now largely unfamiliar to us, because most of them went extinct, either in the Ordovician Extinction or in later crises, leaving the modern oceans to their more familiar inhabitants. To stand on the floor of the Ordovician Sea would be to stand in a world that looks, in its basic structure, like a modern shallow water marine environment: reefs, open sandy areas, deeper basinal environments, but is populated entirely by strangers. The brachiopods were everywhere. These lamp-shelled animals with their two valves, superficially resembling clams but entirely unrelated to them, were the most abundant large invertebrates of the Ordovician seafloor. They came in hundreds of species. They attached themselves to the reef with a fleshy stalk. They clustered in dense banks on sandy substrates. They perched on the stalks of crinoids, hitching a ride above the seafloor to get access to better feeding currents. Their shells are found in Ordovician rocks all over the world, sometimes in layers literally made of nothing else. Limestone composed almost entirely of compressed, interlocking brachiopod shells, representing the accumulated remains of populations too dense to imagine. The brachiopod shell was a beautiful thing, not beautiful in a flamboyant, tropical fish way, but beautiful in the way of a well-made object, symmetrical, precisely constructed, with a surface ornamented by ribs and growth lines that recorded every year of the animal's life, the way tree rings record the life of a tree. The shell was made of calcium carbonate, the same mineral as limestone and chalk, secreted by the mantle of the animal inside it. It was the animal's house and its protection and, eventually, the most reliable evidence it left behind in the fossil record. Crinoids, sea lilies, were the most conspicuous animals of the Ordovician reef environment. They look like plants, but they are animals. Their feathery arms spread from a central cup, filtering plankton and organic particles from the passing water. They attach to the seafloor by a long stalk of calcite discs, the ossicles that could be meters long in the largest species. In the Ordovician, crinoid gardens covered vast areas of the shallow seafloor, their stalks swaying gently in the current, their arms spread wide, a forest of living filters rising above the brachiopod and bryozoan carpet of the bottom. When a crinoid died, its stalk and arms fell apart into their component ossicles, and those ossicles accumulated on the seafloor in thick layers. The crinoidal limestones of the Ordovician pale gray rocks, composed largely of tiny, wheel-shaped calcite discs, are the compressed remains of those fallen crinoid gardens, the geological memory of a world where crinoids were so abundant that their deaths produced limestone. The bryozoans, tiny colonial animals that built delicate, Lace-like or branching structures of calcite were also characteristic of the Ordovician reef. A single bryozoan colony might contain thousands of individuals, each living in its own tiny tube and extending a crown of tentacles to feed. The colonies built structures that look, under a microscope, like miniature cities, rows and streets of identical dwelling tubes, each occupied by a feeding polyp no larger than a grain of sand. The whole colony might be the size of your hand, or the size of a dinner plate, or in some species as large as a small bush. The bryozoan thickets of the Ordovician reef provided shelter for countless other small organisms, worms and small crustaceans and tiny echinoderms, nestling in the spaces between the bryozoan branches. The trilobites, those iconic arthropods that had been the most famous animals of the Cambrian, were still present in the Ordovician and still diverse, though they were no longer the dominant organisms they had once been. They crawled across the seafloor in search of food, rolled into defensive balls when threatened, and left their shed exoskeletons in the sediment as evidence of their molting. The Ordovician trilobites came in a remarkable variety of forms. Some were small and simple. Others were elaborate, with eyes mounted on stalks, or with long spines projecting from every segment, or with bizarre, flattened bodies designed for swimming in the open water rather than crawling on the bottom. Graptolites were among the most distinctive and most scientifically useful of the Ordovician organisms. These colonial animals lived in floating colonies, suspended in the open ocean, their tiny, feeding individuals arranged along a spine or a series of branches. Their colonies looked like nothing else in the living world, some like tiny hacksaw blades, some like tuning forks, some like complex branching trees. They drifted in the surface waters of the Ordovician Ocean in vast numbers, and when they died, they sank to the sea floor and were preserved in the fine-grained sediment of the deep basin as flat, carbonized films. The graptolite fossils in black shales are so characteristic of their time that geologists use them as index fossils, organisms whose presence in a rock tells you, with precision, exactly when that rock was formed. The nautiloids, those straight and coiled shell-bearing cephalopods, cousins to the modern nautilus, were the apex predators of the Ordovician Sea. Some were small, but the largest were giants, straight-shelled creatures up to 6 meters long, their bodies contained in a tapering cone of shell, their tentacles trailing behind them as they moved through the water by jet propulsion. These orthocone nautiloids were the largest animals in the Ordovician Ocean, and they would have been terrifying to any smaller creature in their path. They hunted with their tentacles, seizing trilobites and smaller cephalopods and whatever else they could catch. The early echinoderms of the Ordovician were far more diverse than the modern echinoderm fauna. In addition to the crinoids already mentioned, there were blastoids, small, round-bodied animals with delicate feeding grooves, edrioasteroids, disc-like animals that lay flat on the seafloor, cystoids, bag-like animals with complex pore systems, and many other groups that are now completely extinct, that left no descendants in the modern world, that exist only as fossils in the limestone of the Ordovician. The echinoderms of the Ordovician were, as a group, stranger and more various than anything in the modern ocean. This was the world that was about to be destroyed, rich, diverse, ancient, perfectly adapted to its warm, clear, shallow water existence, and completely unprepared for what was coming from the south. The architects of the ancient reef, the reefs of the Ordovician, deserve special attention because they were among the most complex and beautiful structures in the history of life and among the most vulnerable when the extinction came. The Ordovician reefs were not coral reefs in the modern sense. The scleractinian corals that build all modern coral reefs had not yet evolved. They would not appear until after the Permian extinction, 200 million years in the future. The reef builders of the Ordovician were different organisms entirely: stromatoporoids, tabulate corals, rugose corals, bryozoans, and calcareous algae, working together in a community of mutual interdependence that produced structures of remarkable size and complexity. The stromatoporoids were sponge-like organisms, or perhaps true sponges. The classification is debated, that built solid calcareous skeletons in a variety of forms. Some were flat, encrusting sheets that covered the seafloor with a hard calcium carbonate pavement. Others built domed or columnar structures, rising from the seafloor in rounded mounds. Still others grew in branching or irregular forms, their surfaces covered with a distinctive pattern of pores and canals through which water circulated, carrying food to the living tissue within. The stromatoporoids were the primary frame builders of the Ordovician reef, the architects, the structural engineers, the organisms whose solid skeletons provided the foundation on which everything else was built. The tabulate corals were colonial animals, closely related to modern corals in their basic biology, but with a different skeletal structure. They built colonies of small polygonal tubes, the corallites arranged side by side in sheets or domes, their horizontal partitions dividing each tube into a stack of chambers. The tabulate corals built reefs, not as large as the stromatoporoids, but significant contributors to the reef framework, adding their calcareous skeletons to the growing structure and providing shelter and attachment surfaces for hundreds of other organisms. The rugose corals were the other major coral group of the Paleozoic solitary animals, mostly with a single horn-shaped skeleton whose internal structure was more complex than the tabulate corals. The rugose corals were not reef builders in the strict sense, but they were common inhabitants of the reef environment, colonizing the rubble around the base of the reef and the sandy patches between the reef structures. Their large, isolated skeletons are among the most beautiful fossils of the Paleozoic, simple in outline, but complex in their internal structure, like cross-sections of a tiny cathedral. The bryozoans, as noted, were essential contributors to the reef community. The fenestrate bryozoans, with their fan-shaped, lace-like colonies, were characteristic of the Ordovician reef environment, their delicate structures providing surfaces for smaller organisms and trapping sediment among their branches, helping to solidify the reef framework. The branching bryozoans formed thickets in the spaces between the larger reef builders, creating a three-dimensional habitat of extraordinary complexity. And in all the spaces and crevices and shadows of this reef, in the gaps between the stromatoporoids and under the ledges of the tabulate coral colonies, and among the branches of the bryozoan thickets, lived an extraordinary diversity of smaller organisms, small trilobites, their compound eyes scanning the shadows, tiny brachiopods cemented to the reef surface, gastropods grazing on the film of algae that covered every available surface, ostracodes, tiny crustaceans in bivalved shells swarming through the water just above the reef surface, worms, invisible but omnipresent, processing the sediment and the organic matter that accumulated in every crevice. The Ordovician reef was a city, a living city, built over millions of years by the accumulated work of billions of organisms, each one adding its tiny contribution to the structure. A grain of calcium carbonate here, a millimeter of skeleton there, until the whole became something vast and complex and self-sustaining. Some Ordovician reef structures were hundreds of meters across and tens of meters high. They had been growing, in some cases, for millions of years. They were among the most durable and most complex biological structures the world had ever seen. They had never experienced an extinction. They had no evolutionary memory of one, and they were entirely unprepared for what the cooling of the climate was about to do to them, the first vertebrates and their strange world. Among all the creatures of the Ordovician Sea, one group deserves special mention, not because it was the most abundant or the most ecologically important, but because it was the beginning of a lineage that would eventually produce every vertebrate on Earth, including the animals in every bed and on every pillow, in every room where this documentary is playing tonight. The first vertebrates appeared in the Cambrian, but they diversified significantly in the Ordovician. They were the agnathans, jawless fish, animals with a backbone and a skull, but without the hinged jaws that would characterize all later fish and all land vertebrates. The agnathans of the Ordovician were small. Most were no larger than a modern minnow, and the largest were perhaps the size of a small trout. They were not fast swimmers. They were not impressive predators. They were, in many ways, the least remarkable animals in the Ordovician Sea. But they had a backbone. They had a skull. They had eyes, real, image-forming eyes, more sophisticated than the simple light-sensitive patches of many invertebrates. They had a nervous system centralized in a brain, a small brain, simple by any later standard, but a brain nonetheless. And they had, already, the fundamental body plan that would be inherited, modified, and elaborated over the next 445 million years into everything from sharks to salamanders to birds to human beings. The Ordovician agnathans were armored. Their bodies were covered in plates and scales of bone, the same bone that would eventually migrate inside the body to become the internal skeleton of all later vertebrates. But in the early fish, it was on the outside, a suit of bony armor that protected them from the predators of the Ordovician Sea. These armored fish are called ostracoderms, and they are preserved in Ordovician rocks from several locations around the world, from Siberia, from North America, from Australia, as flat, compressed impressions of their bony armor, beautiful and strange. The ostracoderms of the Ordovician were filter feeders, mostly. They swam through the water, their mouths open, drawing in water and filtering out the plankton and organic particles suspended in it. They were, in ecological terms, something like the anchovies or herring of the Ordovician Sea, small, abundant, filter-feeding vertebrates that were probably important prey for the larger nautiloids and the predatory invertebrates of the reef. They would not survive the extinction. The Ordovician extinction was as devastating for the early vertebrates as it was for every other group, and the ostracoderms that had been establishing themselves in the Ordovician seas were severely reduced. But some survived. Some always survive. And from those survivors, over the tens of millions of years that followed, the vertebrate lineage would continue its slow evolution toward jaws, toward limbs, toward the eventual colonization of the land. Tonight, the ostracoderms of the Ordovician are the ghosts in the story, small, armored, unremarkable, swimming through a doomed world without knowing it is doomed. Their descendants are reading this account. Their descendants survived. Their story continues, right through the extinction and the recovery and the 445 million years that followed, to tonight. The invasion that never came, life at the edge of the land. Before we descend into the extinction, it is worth pausing at the edge of the Ordovician Sea, at the margin between the water and the land, because this is where one of the most significant stories of the Ordovician was playing out, a story that the extinction would interrupt but not end. The land of the Ordovician was not completely bare. As we noted earlier, the first primitive land plants were beginning to establish themselves on the wettest margins of the continents, on the muddy edges of river mouths, on the wet rock surfaces around hot springs, on the thin film of moisture that persisted on north-facing cliffs and in the spray zone of coastal rocks. These were not plants in any recognizable modern sense. They were more like thick crusts of photosynthetic organisms, liverwort-like, moss-like, simple and thin, able to photosynthesize in the daylight and to curl tight and dormant in the dryness of the night or the dry season. The evidence for these earliest land plants comes not from fossils of the plants themselves, but they were too soft and too simple to fossilize readily, but from the spores they produced, preserved in ancient sediments. The spores of Ordovician age are tiny, tough, resistant structures, protected by a polymer called sporopollenin that is essentially indestructible. They can survive in sediment for hundreds of millions of years, and they tell us that plant life was present on the Ordovician land, even if it was sparse and simple. The first land animals were also beginning to venture out of the water. Not vertebrates, those were still thoroughly aquatic, but small arthropods, related to the millipedes, were beginning to exploit the thin film of life that the first land plants had established. The evidence for them is similarly indirect trace fossils, the preserved trackways of tiny animals moving across wet mud surfaces that were then lithified into rock. These tracks tell us that something was crawling on the Ordovician land, something arthropod-like and small, making its cautious, exploratory way across a world that was not yet ready for it. The Ordovician colonization of the land was a beginning, not an achievement. It was the first hesitant steps of a process that would take another 50 million years to produce truly complex terrestrial ecosystems. But the steps were being taken, and the extinction, when it came, would slow this process. The disruption of the Ordovician world would set back the colonization of the land, just as it set back everything else. But it would not stop it. Nothing stops life for long. The cooling begins. Gondwana drifts toward the pole. The trigger for the first apocalypse was not an asteroid. It was not a volcano, at least not in the primary role. It was something slower and more inexorable, the movement of a continent. Gondwana, that vast southern supercontinent, larger than any landmass in the modern world, was moving. It had been moving for millions of years, as all continents always move, carried by the slow convection of the mantle beneath the crust. And in the late Ordovician, Gondwana was moving south. The leading edge of the supercontinent, the part that corresponds to what is now North Africa and the Sahara, was drifting toward the South Pole. This drift had consequences. Continents at the poles cool down. The ice that forms on a polar continent reflects sunlight back into space rather than absorbing it, which cools the planet further. The cooled ocean water that surrounds a polar continent sinks to the deep ocean, driving a vigorous thermohaline circulation that redistributes heat around the globe. The growth of ice sheets locks up water that would otherwise be in the ocean, lowering sea level. All of these consequences operated in the late Ordovician. As Gondwana drifted over the South Pole, the southern margin of the supercontinent began to cool. Snow accumulated, and some of it persisted through the summer rather than melting completely. Year by year, century by century, the snow compacted into glacial ice. The glaciers grew. Ice sheets formed, first small and tentative, then larger, then enormous ice sheets that would eventually cover an area comparable to the modern Antarctic ice sheet, spread across the southern portions of what is today Africa and South America. The growth of the Gondwana ice sheets began approximately around 447 million years ago, about 2 million years before the main extinction event. It was slow at first. The early glaciation was modest, the ice sheets small, the climate signals subtle, but the ice sheet, once established, had its own momentum. Ice reflects sunlight. Less sunlight absorbed means less heat, which means more ice. The positive feedback loops of glaciation, the same feedback loops that have driven every ice age in Earth's history, kicked in, and the cooling accelerated. The CO2 level in the atmosphere was already falling before the glaciation began. The Ordovician world had been a greenhouse world, with CO2 levels many times higher than today. But over the course of the Ordovician period, the geological processes that draw CO2 out of the atmosphere, the weathering of silicate rocks, which converts CO2 to bicarbonate and carries it to the sea, had been operating more efficiently than the volcanic processes that release CO2. The net result was a slow, millennial drawdown of CO2 that gradually weakened the greenhouse effect. Some researchers also point to the Ordovician as the time when land plants first significantly altered the atmosphere's CO2 content. The earliest land plants, the liverwort-like organisms that were establishing themselves on the wet margins of the Ordovician continents, were photosynthesizing, pulling CO2 from the atmosphere and storing it in organic matter. More importantly, they were beginning the process of biological weathering, their root-like structures penetrating rock, releasing organic acids that dissolved the minerals and accelerated the drawdown of CO2. If the land plants of the late Ordovician were already having a measurable effect on the CO2 budget, and the evidence is disputed but suggestive, then the cooling that triggered the Ice Age may have been, in part, a biological phenomenon, life cooling its own world. Whatever the precise cause of the initial cooling, the consequences were clear. The ice sheets grew, the climate cooled, and the warm, shallow, tropical seas of the Ordovician began to change. The ice sheets that ended an age. The ice sheets of the late Ordovician glaciation, the Hernantian glaciation, named for the final stage of the Ordovician period, were among the largest in Earth's history. Some estimates suggest that they were comparable in extent to the ice sheets of the last glacial maximum, the Pleistocene Ice Age, that ended 12,000 years ago, or even larger. They covered the southern portions of Gondwana in ice, perhaps 2 to 3 kilometers thick, a weight that pressed the underlying rock downward and created a depression that would persist for millions of years after the ice melted. The direct effect of the ice sheets on the organisms of the Ordovician was mostly indirect. The ice was on the land, far to the south, and the animals of the Ordovician were in the sea, but the ice affected the sea in profound and devastating ways. The most immediate effect was on ocean temperature. The formation of the Gondwana ice sheets drew cold air and cold meltwater into the Southern Ocean, cooling the high-latitude seas dramatically. This cooling was not limited to the high latitudes. The thermohaline circulation, the global conveyor belt of ocean water, driven by the sinking of cold, dense water at the poles, redistributed the cold throughout the global ocean. Tropical seas that had been warm for millions of years began to cool. The temperature of the Ordovician tropical ocean which had been perhaps 40 to 45 degrees Celsius at the sea surface, hotter than any modern tropical ocean, dropped by perhaps 5 to 10 degrees. That sounds small. It was not small. The organisms of the Ordovician reef had evolved in warm water. Their physiology, their reproduction, their growth rates, their calcification, all were calibrated to the warm, carbonate-rich, stable conditions of the tropical Ordovician Sea. A drop of 5 degrees is the difference between a comfortable bath and a cold shower. For a coral polyp or a bryozoan colony whose entire metabolic machinery is optimized for warm water, a sustained temperature drop of that magnitude is lethal. The calcification of reef-building organisms, the process by which they extract calcium carbonate from seawater and incorporate it into their skeletons, is temperature dependent. Cold water holds more CO2 dissolved in it, which makes it more acidic, which makes calcium carbonate less stable and harder to precipitate. As the Ordovician Ocean cooled, the calcification of the reef builders slowed, their growth rates dropped, their skeletons became thinner, more fragile. The reefs that had been growing steadily for tens of millions of years began to slow their construction, and then to stop, and then, as the organisms that built them died, to begin to dissolve. The cooling also changed the circulation of the Ordovician Ocean in ways that were deeply damaging to shallow water marine life. A well-circulated, oxygenated ocean maintains high oxygen levels in shallow water, which most marine organisms need. When the ocean circulation changes, when the thermohaline conveyor slows or redirects its flow, some areas can become oxygen depleted. The evidence in the geological record of the late Ordovician suggests that widespread anoxia, the depletion of dissolved oxygen, affected many parts of the shallow and deep ocean during the glacial maximum, killing organisms that could not survive without adequate oxygen. The ice was growing in the south. The ocean was cooling throughout. The oxygen was declining in many areas. And then the sea level began to fall. The sea level falls. A world of shrinking oceans. The growth of the Gondwana ice sheets required an enormous quantity of water. Water that had been in the ocean, cycling through the atmosphere, falling as rain, flowing through rivers. All of this water was now being captured by the growing ice sheets, compressed into glacial ice, and stored on the continent. As the ice sheets grew, the ocean became smaller. The sea level fell. The fall in sea level during the Hernantian glaciation was significant. Estimates range from approximately 50 to 100 meters, though some researchers suggest it may have been even greater. 100 meters of sea level fall is a massive change. The continental shelves, the shallow platforms that rim the continents, extending outward from the coastline to depths of a few hundred meters, would have been largely or entirely exposed. The epicontinental seas, those shallow, warm interior seas that had covered large areas of the continents and supported the richest communities of Ordovician marine life, would have drained away. Imagine the epicontinental sea that covered most of North America in the Ordovician, the warm, clear, shallow water that lapped over what is today Ohio and Kansas and Missouri. As the sea level fell, this water retreated, slowly at first, then faster as the glaciation intensified. The reefs and brachiopod banks and crinoid gardens of the epicontinental sea found themselves in shallower and shallower water until the reef crests were exposed to air that the reef builders could not breathe, air that dried the exposed tissue of the coral polyps and the bryozoan colonies, air that was simply death to organisms that had never in their evolutionary history been out of the water. The exposed reef crests died. The reef organisms below the exposed crests continued living for a while. The water was still there, still warm enough, still oxygenated enough, but the reef structure was being undermined from above. The cap was dead, and without continued growth at the top, the reef framework began to weaken. The framework organisms, the stromatoporoids, and the tabulate corals needed to keep growing to maintain the reef against the constant erosion by waves and biological borers. When growth stopped, erosion won. The falling sea level also changed the nature of the sea floor across the exposed shelves. The areas that had been underwater were now land, not vegetated. Productive land, like the modern exposed shelf environments, would eventually become, but bare, waterlogged, saline mudflats, exposed to the unfamiliar alternation of sun and wind. The sediment on these flats dried and cracked. The organic matter in the surface sediment was oxidized, releasing CO2 back into the atmosphere. The evaporation of water from the exposed shelves concentrated the remaining salts, creating hostile conditions for any organisms trapped in the receding water. The communities of the Ordovician shallow sea were fragmented. The wide, continuous, shallow platform that had supported a single, interconnected community of organisms across entire ocean basins was broken up into smaller, isolated patches, remnant seas in the deepest basins, isolated from each other by the bare, exposed shelf between them. Species that had been connected across a vast geographic range were now isolated in smaller populations, separated from each other, unable to interbreed or to receive colonists from elsewhere when local conditions became difficult. Small, isolated populations are vulnerable. They are vulnerable to random events that kill too many individuals too fast. They are vulnerable to inbreeding, which reduces genetic variation and therefore reduces the ability to adapt to changing conditions. They are vulnerable to local environmental changes that would be easily survived by a large, geographically distributed population, but that can drive a small, isolated population to extinction. The fragmentation of the Ordovician Sea by the falling sea level was a death sentence for many species, even before the coldest temperatures arrived. The cold that killed, the glacial maximum of the Hirnantian, the peak of the Ordovician Ice Age, when the ice sheets were at their largest and the sea level was at its lowest and the ocean temperatures were at their coldest, was the first blow of the two-blow extinction. In the warm, tropical seas of Laurentia and Baltica, the temperature drop was significant enough to kill many of the organisms adapted to the extreme warmth of the pre-glacial Ordovician. These warm-adapted organisms, the high-temperature specialists of the Ordovician reef, could not survive in water that had cooled by 5 to 10 degrees from their preferred range. They died, their populations crashed, their communities dissolved. But not everything died. Some organisms were tolerant of a wider range of temperatures. Some populations, living in the slightly cooler waters of higher latitudes, had already adapted to temperatures somewhat below the tropical maximum. These organisms, the generalists, the cool water adapted, the tolerant, survived the initial cooling, and in surviving, they inherited the ecological space vacated by the warm-adapted specialists. This produced one of the most striking phenomena in the Ordovician extinction record, the Hirnantian fauna. This was a distinctive assemblage of brachiopods and other organisms that colonized the shallow seas of the glacial maximum, a cool adapted community that spread across the tropical and subtropical regions during the glacial peak, replacing the warm water communities that had died out. The Hirnantia brachiopod, the dominant species of this fauna, giving its name to the entire assemblage, was a relatively simple, robust brachiopod, tolerant of cold water and low food availability, capable of surviving in conditions that the more elaborate warm water specialists could not endure. The Hernantian fauna spread widely in a geological instant across the cooled Ordovician seas. It was not diverse. It was dominated by a relatively small number of opportunistic, cold-tolerant species, but it was abundant, and its abundance obscures, in the fossil record, the true extent of the destruction, because the Hernantian fauna fills the stratigraphic gap between the rich communities of the pre-glacial Ordovician and the sparse communities of the post-glacial Silurian, giving the impression of continuity where there was, in fact, massive disruption. Beneath the spread of the Hernantian fauna, the deep seas were dying differently. The deep ocean of the glacial maximum was increasingly anoxic. The changed circulation patterns were delivering less oxygen to the deep basins, and the respiration of bacteria decomposing the organic matter raining down from the surface was consuming what little oxygen remained. The black shales of the late Ordovician, the dark, organic-rich sediments that indicate anoxic conditions, record this deep water deoxygenation. The organisms of the deep Ordovician sea, whatever they were, and the fossil record of the deep ocean is always sparse, were dying in the darkness for lack of oxygen. The graptolites, those floating colonial animals that had been among the most abundant organisms in the Ordovician open ocean, were catastrophically reduced. They had been extraordinarily diverse in the Ordovician, producing hundreds of species in a variety of branching and non-branching forms. The cold waters and the changed ocean chemistry of the glacial maximum were unfavorable for them. Most of their lineages disappeared. The few that survived into the Silurian were a tiny remnant of their former diversity. The nautiloids, the great straight-shelled predators of the Ordovician, also suffered severely. Not all of them died. The coiled nautiloids, in particular, were relatively resilient, and their lineage continued into the Silurian and beyond, eventually producing the modern nautilus. But the enormous orthocone nautiloids, the giants of the Ordovician, were reduced. Their populations crashed as the ecosystems they depended on collapsed. Some survived, smaller and less diverse than before. Others were gone. The trilobites, those ancient arthropods that had been present since the Cambrian, lost a significant portion of their diversity in the Ordovician extinction. Many families disappeared entirely. Others were severely reduced. The trilobites that survived into the Silurian were a shadow of the Ordovician diversity, and they never fully recovered. The Ordovician extinction was not the death blow for the trilobites they would struggle on for another 200 million years, but it was the beginning of their long decline. The echinoderms, those diverse and ornate creatures of the Ordovician seafloor, also suffered badly. The cystoids, the blastoids, the edrioasteroids, the many strange and specialized echinoderm groups of the Ordovician were reduced or eliminated. The crinoids survived, though reduced. The starfish and sea urchins survived. But many of the more exotic echinoderm groups that had made the Ordovician seafloor so strange and rich were gone or going. The second blow, when the ice melted too fast, If the story of the Ordovician extinction ended at the glacial maximum, at the peak of the cold, the lowest sea level, the coldest ocean, then perhaps it would be a simpler story. Cold conditions killed the warm-adapted organisms. Cool-adapted organisms spread in their place. Eventually, the glaciation ended, the world warmed, and the cool-adapted organisms evolved into warm-adapted ones, and life recovered. But the story did not end there. The Ordovician extinction has two pulses, and in some ways, the second pulse was more devastating than the first. The second pulse of extinction occurred when the ice melted, when the Gondwana ice sheets, having reached their maximum extent, began to retreat, retreating relatively rapidly by geological standards. Over the course of perhaps 1,000,000 years, the consequences for the surviving marine communities were almost as bad as the consequences of the glaciation itself. The sea level rose rapidly. The meltwater that the ice sheets had been storing for millions of years was returned to the ocean in a geological eye blink, raising the sea level by tens of meters over hundreds of thousands of years. The epicontinental seas reflooded, the shelves were inundated again. The bare mudflats that had formed on the exposed shelves were covered by the rising ocean. This flooding brought problems. The water that returned to the epicontinental seas was different from the water that had left. It was colder, carrying the thermal memory of the glacial ocean. It was differently oxygenated. The rising sea level drowned the organic matter that had accumulated on the exposed shelves, and as this organic matter decomposed, it consumed oxygen from the water. The returning sea was full of sediment, the material eroded from the exposed shelves by wind and rain during the glacial maximum, now being mobilized by the rising water and carried into the returning epicontinental basins. More critically, the warm, oxygenated surface waters and the cold, anoxic deep waters of the glacial ocean were mixing as the circulation changed with the warming. The anoxic water from the deep ocean, enriched in the toxic hydrogen sulfide produced by anaerobic bacteria in the absence of oxygen, was being upwelled into the shallow seas as the ocean circulation reorganized. The Hernantian fauna, those cool-adapted, hard-won survivors of the glacial maximum, found themselves in water that was becoming warmer and simultaneously deoxygenated. They had survived the cold. They could not survive the warmth combined with oxygen deprivation. The Hernantian fauna collapsed. Its species, having spread across the cooling ocean during the glacial maximum, now found themselves in conditions they could not survive. The Hernantia brachiopod, which had been so abundant, so widespread, the dominant organism of the glacial maximum ocean, essentially disappeared. Its populations crashed. The other members of the Hernantian fauna went with it, and the warm-adapted organisms that might have replaced it, the rich communities of the pre-glacial Ordovician, the brachiopod banks and the crinoid gardens and the reef builders were gone, or mostly gone. The survivors were a tiny fraction of the pre-extinction diversity, scattered in small populations in the refugia where conditions had been slightly more tolerable throughout the double blow of cold and warming. The two-pulse structure of the Ordovician extinction is what made it so devastating. A single cooling event or a single warming event might have killed the temperature-sensitive specialists while allowing the generalists and the moderate temperature organisms to survive. But the combination cold that killed the warm-adapted, followed by warming that killed the cold-adapted, created a situation where almost no organism could survive both pulses. The organisms that had been pre-adapted to cool water were killed by the warming. The organisms that had been pre-adapted to warm water were killed by the cooling. The survivors were the very few, the very lucky, the very flexible. What died and what was lost forever. Let us be specific about what was lost, not in the abstract language of percentages and species counts, but in the concrete terms of specific organisms and specific ways of life that the world has never seen again. The stromatoporoids, the primary reef builders of the Ordovician, were devastated. They did not go extinct entirely in the Ordovician extinction. They survived, reduced into the Silurian and Devonian, where they rebuilt their reef-building role. But the great stromatoporoid reefs of the Ordovician, those thick, solid, multi-meter structures built by hundreds of thousands of years of colonial growth, were gone. The specific communities that had assembled around them, the specific ecological relationships that had developed in and around those reefs over millions of years, were gone. They could not simply be reconstituted when the survivors began to rebuild. The reef of the Silurian was a different reef, assembled by different organisms in different proportions, with different inhabitants and different ecological dynamics. The tabulate corals were severely reduced. Many families disappeared. Those that survived were fewer in species and more restricted in their distribution. The diverse, complex tabulate coral communities of the Ordovician, with their different growth forms, their different colony sizes, their different ecological roles, were simplified. What survived was a smaller, less varied community of tabulate corals that rebuilt slowly in the Silurian. The rugose corals also suffered, losing many lineages. The elaborate, ornate, solitary rugose corals of the Ordovician, some of them enormous, their single skeletons half a meter across, were reduced to smaller, simpler forms. The specific morphological elaborations that had evolved in the rugose corals over tens of millions of years of the Ordovician were largely lost. The complex internal structures simplified, the variety of external forms reduced to a few basic types. Among the brachiopods, the losses were selective but significant. Some families survived quite well. The strophominid brachiopods, in particular, were resilient and recovered relatively quickly. Others were devastated. The orthid brachiopods, one of the most diverse and long-established brachiopod groups, lost many lineages. The pentamerid brachiopods, which had been becoming increasingly important in the later Ordovician, were essentially eliminated, their promising early evolution cut short by the extinction. The graptolites, those extraordinary floating colonial animals of the open ocean, lost the vast majority of their diversity. Of the hundreds of Ordovician graptolite species, only a handful survived into the Silurian. These survivors were not representative of the pre-extinction diversity. They were the most resilient, the most adaptable, the ones with the widest tolerance for different conditions, the most elaborate, the most specialized, the most ecologically particular graptolite species were gone. The Silurian graptolites were a simplified remnant, and though they diversified again in the Silurian, they never fully recaptured the complexity of the Ordovician graptolite fauna. The conodonts, eel-like, soft-bodied creatures that are known almost entirely from their tiny, complex, tooth-like elements, suffered a significant loss of diversity in the Ordovician extinction. Conodonts are important to geologists as stratigraphic tools. Their tooth elements are so distinctive and so geologically short-lived that they can be used to correlate rock layers across vast distances. The Ordovician extinction is marked clearly in the conodont record by a dramatic reduction in diversity, followed by a slow recovery in the Silurian. The early vertebrates, those small, armored, jawless fish that were the ancestors of everything with a backbone, were also hit hard. The fossil record of Ordovician vertebrates is sparse, and the record of their extinction is correspondingly imprecise. But the diversity of ostracoderms in the Silurian is lower than it was in the Ordovician, and the recovery of vertebrate diversity was slow. Whatever promise the early Ordovician vertebrates showed whatever evolutionary trajectories they were exploring, whatever niches they were beginning to occupy, was disrupted by the extinction. What was lost was not just species and genera. What was lost was ecological complexity. The Ordovician Sea had been a place of extraordinary ecological sophistication, of complex food webs, of intricate reef communities, of specialized relationships between organisms that had evolved over millions of years of coexistence. That sophistication took tens of millions of years to rebuild. The Silurian world, even at its most productive and diverse, was simpler than the Ordovician world it replaced, less species-rich, less ecologically complex, less intricately organized. The first apocalypse did not destroy life, but it destroyed the specific, particular, beautiful version of life that the Ordovician had assembled, and that version was gone, forever. What came after was different, sometimes equally beautiful, eventually more complex, eventually more diverse, but it was not the same. The specific organisms, the specific relationships, the specific communities of the Ordovician were finished, replaced by something new that grew from the survivors' slow, patient rebuilding. The survivors in the deep and the dark. Where did the survivors hide? What corner of the dying Ordovician Sea was hospitable enough, stable enough, lucky enough to shelter the organisms that would eventually repopulate the world? The answer, as it always is in mass extinctions, is the margins, the edges of the catastrophe, the places where the conditions were slightly less extreme, slightly more stable, slightly more forgiving than the areas that were most directly hit. One set of refugia was in deeper water. The shallow seas, the epicontinental seas of the continental shelves, were the most severely affected environments in the Ordovician extinction. They experienced the full force of the sea level fall. They drained away. The organisms that lived in the deeper parts of the ocean, basins at depths of hundreds of meters below the level of the sea level fall, in water that remained present even as the shallows drained, were protected from the most immediate cause of death. But deeper water brought its own problems. The deep ocean was increasingly anoxic during the glacial maximum. The organisms that lived there needed to be tolerant of low oxygen levels, or they needed to find the specific patches of deep water where oxygen was still adequate. Some organisms could survive in low oxygen conditions. Indeed, some thrived there, because the anoxia that killed their competitors reduced predation, pressure, and competition for resources. These low oxygen tolerant organisms became the survivors of the deep. Among the graptolites, the survivors were those species that lived at intermediate depths, not the shallowest species, which were most exposed to the effects of the glaciation, but not the deepest either, where anoxia was worst. The few surviving graptolite lineages of the Hernantian are found in rocks that suggest moderate depths, in water that was oxygenated but not warm, the Goldilocks zone of the Ordovician extinction. Another set of refugia was in geographically protected areas. Not all parts of the Ordovician Ocean were equally affected by the extinction. Areas near the equator where the ocean remained relatively warm, even during the glacial maximum, were somewhat protected. Areas with specific local oceanographic conditions, upwelling of nutrient-rich, deep water, proximity to volcanic activity, that warmed the local water may have been slightly better than the average, and areas that were, for geographical reasons, somewhat isolated from the worst effects of the changing circulation in closed basins, partially restricted seas, may have maintained conditions that were tolerable, while the surrounding open ocean was in crisis. The survivors in these refugia were not simply waiting out the storm, passively enduring the bad conditions until things improved. They were evolving. The intense selection pressure of the extinction was driving rapid evolutionary change in the surviving populations. The organisms that were best able to tolerate the cold, the low oxygen, the changed water chemistry, the reduced food supply, these were the ones that reproduced most successfully. Their genes spread through the surviving populations. The populations were changing, generation by generation, in ways that would make them different from their pre-extinction ancestors. In some cases, this rapid evolution in refugia produced new species adapted to the specific conditions of the refuge environment that were genetically distinct from any pre-extinction species. These new species would be part of the founding stock of the Silurian world, carrying the evolutionary innovations of their refuge period into the new conditions of the post-extinction recovery. The survivors were not just the living memories of the Ordovician. They were already the beginnings of the Silurian, the long silence after, the immediate aftermath of the Ordovician extinction, the earliest Silurian, the Rudanian, and Aaronian stages, roughly 443 to 438 million years ago, was a world of extraordinary sparseness. The fossil record of these stages is thin, not just poorly preserved, thin in the sense that there was very little to preserve. The organisms that had populated the Ordovician seas in such abundance were mostly gone. What remained was a small number of species, widely distributed but not particularly abundant, living in a world of empty niches and broken food webs. The seafloor of the earliest Silurian was a place of quiet. The crinoid gardens were gone or reduced to small, scattered patches. The brachiopod banks were thin and simple. The reefs were gone. There would be no significant reefs in the earliest Silurian, only the first tentative attempts at reef building, small and fragile structures that would take millions of years to grow into the reefs of the later Silurian. The trilobites that crawled across the earliest Silurian seafloor were fewer in species, smaller in population, less diverse in form than their Ordovician predecessors. The water above the seafloor was also quiet. The graptolites that had filled the Ordovician open ocean with their drifting colonies were reduced to a handful of surviving lineages, their sparse populations drifting in water that must have seemed vast and empty by comparison with the teeming Ordovician plankton community. The nautiloids were fewer. The ammonoids had not yet appeared. That was still tens of millions of years in the future. The open ocean of the earliest Silurian was a simplified, impoverished version of the Ordovician ocean, but it was not dead. That is the most important thing about the earliest Silurian. The world was diminished, impoverished, simplified, stripped of most of its complexity, but it was not dead. The fundamental processes of the ocean continued. Photosynthesis continued, producing oxygen and organic matter. The food web, however simplified, continued to function. Small organisms were eaten by larger organisms, which were eaten by larger ones still, and the flow of energy through the system continued, reduced but unbroken. The survivors were reproducing. Every generation, new individuals were born into the empty world, facing less competition than their parents had faced, with more resources available per individual than the crowded Ordovician world had provided. The mathematics of ecology are unforgiving in crowded conditions. When niches are full, populations cannot grow, new species cannot establish. But in an empty world, those same mathematics favor growth and expansion. The survivors were in an empty world, and they were expanding into it. The recovery. How the Silurian was born from the Ordovician's ashes. The recovery from the Ordovician extinction was slower than the recovery from some later extinctions, and faster than the recovery from others. It was uneven. Some groups recovered quickly, others took much longer, and some never truly recovered at all. Among the first organisms to begin expanding in the earliest Silurian were the brachiopods, specifically the strophominid brachiopods. The group that had been relatively resilient during the extinction began diversifying rapidly in the Rhodanian and Uronian, producing new species adapted to the new conditions of the post-extinction ocean. The brachiopods were helped by the absence of competition. The niches that other brachiopod groups had occupied in the Ordovician were now empty, available for colonization by whatever species was willing and able to move into them. The strophominids moved in, diversified, and became the dominant brachiopods of the early Silurian. The graptolites showed a similar rapid early recovery. The few surviving lineages, those that had endured the extinction in the refugia of the intermediate depth ocean, began diversifying in the earliest Silurian. New graptolite species appeared. New colony forms evolved. Within a few million years, the graptolite fauna was again diverse, again widely distributed, again useful as stratigraphic tools. But it was a different diversity from the Ordovician. Fewer species, simpler colony forms, a community that had been rebuilt from a tiny genetic foundation and carried the marks of that bottleneck in its reduced variety. The crinoids recovered more slowly. The crinoid gardens of the Ordovician took millions of years to be replaced by anything comparable. The early Silurian crinoids were sparse and simple, but they were there, and they were evolving. And by the middle Silurian, the crinoid gardens were again a characteristic feature of the shallow water reef environment. The reefs were the slowest to recover. The stromatoporoid reefs of the Ordovician had been destroyed, and the organisms that would build the Silurian reefs needed time to diversify and to develop the ecological relationships that made reef building possible. The first Silurian reefs appeared in the Landovery perhaps 5 to 10 million years after the extinction, small and simple, dominated by tabulate corals and stromatoporoids that had survived the extinction in reduced numbers. These early Silurian reefs were nothing like the great Ordovician structures. They were modest small mounds and low-lying encrusting structures, easily missed in the rock record. But by the Wenlock, the middle part of the Silurian, around 430 million years ago, the reefs had grown. The stromatoporoids had diversified again, producing new growth forms. The tabulate corals had recovered enough to play a significant role in reef building. The rugose corals were there, adding their solitary skeletons to the reef rubble and the reef crevices. And a new organism, the calcareous algae, encrusting algae that deposited calcium carbonate on their surfaces, had taken on a more important role in reef building than in the Ordovician. The Silurian reefs were different from the Ordovician reefs, but they were reefs. They were complex, three-dimensional structures that housed communities of extraordinary diversity. They were beautiful, and they were the foundation on which the Devonian world, the next great chapter in the history of marine life, would be built. The vertebrates recovered too, though slowly. The ostracoderms that survived the Ordovician extinction diversified in the Silurian, producing new forms and new adaptive strategies. And in the Silurian, a revolutionary event in vertebrate evolution occurred: the origin of jaws. The jawed fish, the gnathostomes, appeared in the Silurian fossil record, small and rare at first, but carrying within them the innovation that would transform the vertebrate world. With jaws came the ability to bite, to chew, to eat hard-shelled prey, to exploit the entire spectrum of food types available in the marine environment. The jawed fish of the Silurian were the ancestors of every jawed animal alive today. Every shark, every bony fish, every amphibian, every reptile, every mammal, every human being. The Ordovician extinction had not stopped the vertebrate story. It had interrupted it, reduced it, forced it through a bottleneck. But the story continued, and the jaws that appeared in the Silurian were, in a sense, the response to the extinction, the evolutionary innovation that allowed the vertebrates to expand beyond the filter-feeding niche that the ostracoderms had occupied, and to exploit the full richness of the recovering Silurian ocean. What the Ordovician extinction teaches us: the first apocalypse was not caused by anything dramatic. No asteroid crashed into the Earth. No supervolcano blew its top. No alien force disrupted the planet. The Ordovician extinction was caused by a continent moving, by ice forming on that continent, by the water that ice locked up being withdrawn from the sea, by the cold spreading through the ocean and killing organisms that had never experienced cold, and then by the ice melting and the warmth returning, and the organisms that had survived the cold finding themselves killed by the warmth. It is a humbling story. The Ordovician extinction reminds us that the conditions necessary for a rich, diverse, complex living world are not robust. They can be disrupted by processes that are entirely within the normal operation of the planet, processes that are slow by human standards, but fast by the standards of evolution, too fast for species to adapt, too fast for ecosystems to adjust. A continent drifting a few thousand kilometers to the south, carrying an ice sheet in its wake, was enough to nearly destroy the entire community of complex life in the world's oceans. The extinction also teaches us something about the nature of resilience. The organisms that survived the Ordovician extinction were not the ones that were strongest or most dominant before the extinction. They were the ones with the widest ecological tolerances, the broadest diets, the greatest ability to function across a range of conditions. The specialists, the organisms most perfectly adapted to the warm, clear, stable conditions of the Ordovician reef, were the ones that died. The generalists, the ones that could cope with cold, with turbidity, with low oxygen, with reduced food, were the ones that survived. This is a lesson that every mass extinction teaches, and it is a lesson that runs counter to the usual intuition about evolution. We tend to think of evolution as producing ever more specialized organisms, ever more perfectly adapted to their specific niche, and this is true in stable conditions. But in unstable conditions, in the conditions of mass extinction, specialization is a liability. The organism that is perfectly adapted to one set of conditions is perfectly dead when those conditions change. The organism that is imperfectly adapted to many conditions can survive the change, even if it survives in diminished form. The Ordovician extinction also demonstrates the profound importance of the physical world, the geology and the astronomy and the climate in shaping the history of life. The organisms that died in the Ordovician extinction did not die because of anything they did. or because of any failure on their part, or because evolution had somehow gone wrong. They died because a continent moved, because physics and chemistry produced ice, because the ice changed the ocean, because the ocean change killed them. The physical world does not care about the organisms that live in it. It operates according to its own rules, on its own timescales, without regard for the communities of living things that have spent millions of years establishing themselves in its conditions. This is not a counsel of despair, it is a counsel of humility. The living world is embedded in the physical world, dependent on it, shaped by it, vulnerable to its changes. Life has survived every previous disruption of the physical world, every ice age, every volcanic crisis, every sea level change, but it has survived by changing, by evolving, by rebuilding. The old world does not come back. What comes back is something new, built from the survivors, adapted to the new conditions, carrying the marks of the catastrophe in its genetic history. The Ordovician world is gone. The brachiopod banks and the crinoid gardens and the orthocone nautiloids and the strange echinoderms of the Ordovician seafloor are gone, but the survivors rebuilt. The Silurian world that came after the extinction was, in its own way, beautiful, and from the Silurian came the Devonian, with its first forests and its first jawed fish, and the first tentative steps of tetrapods onto the land. And from the Devonian came everything that followed: the Carboniferous, the Permian, the Triassic, the Jurassic, the Cretaceous, the Paleocene, all the way to the world you are lying in tonight. The first apocalypse was real, and life survived it. Not unchanged, nothing survives unchanged, but alive, persistent, determined, in the unconscious, chemical, biological way that life is determined. To continue, to reproduce, to find the conditions that will support it and exploit them, to evolve in response to changing conditions, to build and rebuild and build again, no matter what the physical world throws at it. Epilogue. The stars they never saw. 445 million years ago, in the shallow tropical sea that covered what is now Ohio, a brachiopod was living out its ordinary life. It was not aware of the cooling that was beginning in the south. It was not aware of the ice that was forming on the southern edge of Gondwana. It was not aware that the sea level was beginning to fall, millimeter by millimeter, year by year, in a trend that would, over the course of the next few million years, drain the sea it lived in and leave it exposed to the air it could not breathe. It was simply living, filtering plankton from the warm current that flowed past it, growing its shell slowly, adding one growth line per year, the record of its life written in calcium carbonate, reproducing in the brief, intense spawning events that the Ordovician Sea hosted each spring, releasing its larvae into the water to drift and settle and begin their own quiet lives. It did not know what a star was. It had no nervous system complex enough to have awareness in any sense we would recognize. But the stars were above it, on the other side of the water and the sky, the same stars that are above you tonight, though arranged in different constellations, because the sky has shifted over 445 million years as the solar system moves through the galaxy. The light of those stars was falling on the surface of the Ordovician Sea, filtered by the water to a dim, wavering blue-green illumination that reached the brachiopod in its shallow home. The brachiopod died, not from the extinction it lived, and died before the extinction came, in the ordinary way of all organisms. Its shell fell to the seafloor and was buried by sediment, and over 445 million years of pressure and time, It became part of the limestone of Ohio. Today, if you go to a road cut in central Ohio, you can find brachiopod fossils in the limestone, the preserved shells of animals that lived and died before the extinction came. They are beautiful, these fossils. They are the record of a world that no longer exists, preserved in stone, available to anyone who knows where to look and how to see. They are the first apocalypse made visible, the evidence that it happened, that the world was once different, that the organisms of the Ordovician Sea were real and alive and doing what living things do before the cold came and the sea fell and most of them were gone. You are lying in a world that those brachiopods made possible in a very indirect and very roundabout way. Not because the brachiopods themselves are your ancestors, they are not. Your vertebrate ancestors were the small, armored fish of the Ordovician Sea, and they are another lineage entirely. But because the extinction that killed the brachiopods also shaped the world that your vertebrate ancestors evolved in, the Silurian world, rebuilt from the survivors of the Ordovician extinction, was the world in which the jawed fish appeared. And the jawed fish were the ancestors of everything that came after every vertebrate in the history of the planet, including you. The first apocalypse made you possible, not directly, not in any simple causal chain, but the world that the Ordovician extinction produced. The simplified, recovering, open-niched world of the Silurian was the world that allowed the jawed fish to diversify, allowed the fish to develop into tetrapods, allowed the tetrapods to colonize the land, allowed the land vertebrates to diversify into amphibians and reptiles and mammals, and eventually into the primate lineage that produced you. Every mass extinction in the history of life has, in this sense, made the modern world. Every catastrophe has cleared some ecological space that allowed new forms to emerge. The Ordovician extinction made the Silurian made the Devonian made the Carboniferous, and so on, through 5 great extinctions and countless smaller ones, through ice ages and greenhouse worlds and volcanic crises, through the slow drift of continents and the subtle shifts of orbits, through 4 billion years of change and catastrophe and recovery, to tonight, in the darkness, in the warmth, breathing air that is the product of billions of years of photosynthesis, lying on a planet whose living surface was assembled and reassembled by every crisis in its history tonight. You are the beneficiary of the first apocalypse, of the cold that came 445 million years ago and killed most of what the Ordovician had built. You are the indirect heir of the survivors who endured that cold, who rebuilt the living world from its ruins, who set in motion the chain of recovery and diversification that led, eventually, to you. The brachiopod in the Ohio limestone did not know what a star was, but you do. And the stars that shone on the Ordovician Sea are the same stars, distant, ancient, indifferent, beautiful, that shine on you tonight. The light takes years to reach us from the nearest ones, thousands of years from the more distant, millions from the most remote. The light you see in the night sky is not the present state of the stars. It is the past, arriving at the speed of light, news from a time before you were born, before your species existed, before the dinosaurs, before the first fish, in some cases, before the first complex life. Some of that starlight left its source 445 million years ago. Some of it was traveling through space when the Ordovician Sea was full of brachiopods. Some of it crossed the void while the ice was growing on Gondwana, while the sea was falling, while the reefs were dying. Some of it arrived at Earth's atmosphere while the survivors were rebuilding, while the Silurian was rising from the ruins of the Ordovician, and now it reaches your eyes, or it would if your eyes were open, if it were night, if you were looking up, but your eyes are closing. The darkness is deepening. The story of the first apocalypse is settling into you like sediment, settling through still water, slowly, gently, finding its level. The Ordovician is over. It ended 444 million years ago, and everything since has been recovery and rebuilding and the slow accumulation of complexity that produced the world you live in. The brachiopods of Ohio are fossils. The nautiloids are fossils. The crinoid gardens are limestone. The graptolites are black films on black shale. The first armored fish are compressed bone plates in ancient rock. But you are here, alive, warm, breathing, lying in a world made richer by the catastrophe and the recovery, carrying in your cells the chemical heritage of 4 billion years of life. Your vertebrate backbone, the distant descendant of the backbone of the small armored fish that swam in the Ordovician Sea before the cold came. The first apocalypse happened. Life survived, and here you are. Sleep well. Good night.